All right, thanks very much. So yeah, I'm going to talk about the observed phase angle dependence of the ejecta plume as observed by LICIACUBE and how we can use that to get mass estimates for the ejecta. All right, I'm just going to use the button here because that's not working.
I think on the slides. What we're done.
Okay. All right. Okay, so as I'm sure many of you are aware, NASA's Double Asteroid Redirection Test, or DART, was the world's first successful planetary defense mission, demonstrating the kinetic impactor technique by impacting the asteroid Dimorphos, the moon in the Didymos binary system. The impact and the ejecta plume were observed by the Luke RGB camera aboard the DART companion spacecraft LICIACUBE, as shown in the diagram on the left there. And basically, it separated from the spacecraft just before impact, and then basically observed the plume from in front, from the side, and from behind. And it was basically observing scattered sunlight from the ejecta plume, and the brightness of that changed as it traveled from right to left on that plot. And that's actually a key diagnostic, gives you key diagnostic information, which allows you to key out ejecta mass. Why do we care about ejecta mass? Ejecta mass is critical to understanding the full 3D momentum transfer, asteroid properties, and the effectiveness of the impact in deflecting the asteroid. But to do that well requires accurate knowledge of the ejecta scattering properties, as we showed in our previous paper, because if you don't get that right, your ejecta mass estimates can be off by more than an order of magnitude. So here's a closer look at the geometry of LICIACUBE as it flies past. So DART basically flew in along the y-axis and created the impact plume, and LICIACUBE flies on that parallel trajectory, and you can see that blue line of sight arrow, and then you can see the yellow arrow, which indicates the direction of sunlight, and the angle between them, which is alpha, which is the phase angle. And basically that angle changes as LICIACUBE changes from right to left, and the brightness changes, and that gives us information about the ejecta fragments. And so we can put that together into something called a phase function. So here we've got the angle, the phase angle running around the x-axis, and we've got the reflected brightness, or the geometric albedo, on the y-axis, and you can see that window of the phase angles that were sampled by LICIACUBE in that window in the middle of the plot there. And we compiled a family of phase analogs for particles from the very small to the very large. So we start here with our very small particles in the submicron regime that we created with discrete dipole approximation models, and for irregular and spheroid shaped grains. And you can see that they're sort of sloping upwards and getting brighter with phase angle. We then start looking at particles of larger sizes, and these were created in part from using lab measurements, sort of in the micron and hundreds of micron regime, and then we get into the millimeter regime, again with lab measurements, and also measurements of particles orbiting around Bennu. And then finally, a model for the very large fragments using the Lommel-Zeliger method. And you can see that now the slope is actually pointing in the opposite direction. So you see we have this powerful trend going on here, where as phase angle increases, albedo becomes strongly dependent on grain size. And so we can apply this knowledge to the observations. So here we have an image in the green channel for LICIACUBE at an angle, phase angle of about 51 degrees, with Didymos and Dimorphos outlined in orange there. And you can see there's that black region which outlines, brackets the region where the plume becomes optically thick. Now, as we increase the phase angle, if you look at the images in the scale bars, you can see that the plume brightness is actually starting to get dimmer. And as we keep going, it continues to get dimmer. And bearing in mind what I just said on the last slide, that brightness, the way that brightness diminishes is consistent with millimeter grain size particles. So the next thing we want to do then is basically sort of work out how much light we have in total in each of our images at each of those different phase angles. So we do that by integrating radially outwards from the center of the plume for each of those images. And we know that we've captured all the plume light when the integration basically flattens out, as shown in the curves on the right for two of the observations there, with the associated uncertainties. But how do we put all of this together then to actually get an ejecta mass estimate? Well, we start off with our LICIACUBE observations. We then do our radial integrations for each of those observations at the different phase angles. Oh, the button's... we then basically can use that to produce a radiance versus phase angle plot. And then we get Oh, now it's catching up. We take an optically thin plume model. We put in a particle size distribution with a single power law there without using that power there. We combine that with our phase function models. Let's see if it decides to work now. Nope.
PowerPoint.
All right. And then basically what we can do then is we can do a retrieval process where we fit the radiance, those radiance models to the observations. And this is really handy because basically plume radiant intensity is directly proportional to plume mass. And then that allows us to key out a mass estimate. Now, this is a lower limit. Why do I say a lower limit? Because what we've used is an optically thin model. And the reality is that the inner region of the plume is optically thick, as you saw in the previous observation. So we're not accounting for all the mass. So we basically do that for each of the RGB channels. So the measured radiance is spatially integrated over the Lake field of view and compared with single power law models. Now, the Hubble observations in the ground base, folks, saw broken power laws. And this is likely due to solar radiation pressure size sorting processes. But the thing is, because our observations were so quick after the impact, those processes likely haven't had time to take effect. And so we found that a single power law, unbroken power law, was actually the best fit in terms of the retrievals. So our plume radiance grain radii are in the 100 micron to 1 millimeter size, and they're consistent with the results from the literature. So we basically repeated that analysis for each of the red, blue, and the green channels, which you can see on the left there, where the points show you the integrated plume radiances and the line shows you the model fits. And so that gives you a plume mass for like 3 semi-independent estimates, which seem to be fairly consistent with each other. So that gives you plume mass estimates in the range of 0.79 to 1.13 times 10 to the 7 kilos. But this is a low limit because of that optically thin assumption that I was mentioning. So thank you. So what we can do then is we can do comparisons with multiple scattering models to get an estimate of a mass enhancement because of that optically thick portion of the plume. And so the way you do that is you take the plume brightness, and for a given plume brightness, you can compare a single scattering model and a multiple scattering model, and you can look at the difference in geometrical optical depth. And then you can basically use that to give you an idea of what the mass enhancement is. Again, though, this is a low limit because you can see that's an asymptote for the multiple scattering case. So we worked that out that there was a mass enhancement of at least 1.2 times 10 to the 6 kilos on top of the mass that we'd observed. So summing up then, the brightness of the plume was measured by Luke in the RGB channels is investigated as a function of phase angle. Between 50 degrees and 110 degrees, the measured phase slope of the plume brightness is consistent with a broad maximum in grade radius of near about 1 millimeter in size. The retrievals show that a single power law at the time of the Luke observation, unlike the later observations of Hubble and ground-based folks, where solar radiation pressure seemed to have had some size sorting effects and gave a broken power law. The plume mass present within the Luke field of view is estimated to be 0.79 to 1.13 times 10 to the 7 kilos. I will say that's also consistent with other estimates as well. But this is a low limit because of that optically thin assumption. However, we can make a mass enhancement estimate that adds additional mass for the optically thick portion of the plume, which would be at least 1.2 times 10 to the 6 kilos. And so our ejected mass estimates are consistent with the gravity regime impact, which makes sense because it's believed that Dimorphos is a rubble pile asteroid. And we were able to reach that conclusion by comparisons with recent work from Cheng et al. 2024, where they basically did modeling looking at asteroid cohesive strength versus ejecta yield. And we have a manuscript in progress. So I hope that you realize the importance of ejecta mass and how critical that is to getting the full 3D momentum transfer and how important that information is for planetary defense. And with that, I'd like to thank you very much for listening.